We continue with our exploration of compact spaces and recall that we introduced the preliminaries of the compactness notion and said what compact spaces are and what their properties are. Now it's time to do analysis on this. So what we look at now is what happens when you take up continuous functions on compact spaces. So we have this problem, namely you have a vector space or a not vector space or you call metric space and another metric space. These are two metric spaces with the respective metrics on that. Now we look at a map from a function from x to y. Now we assume x is compact. What one can say about f? Now you see that to recall the following, consider the example. It's like f from some compact interval AB into. Now you know that it's closed and bounded, therefore it is compact. Now this is compact. And we assume f is continuous. Now, what one can say or what appears to be true is this. Suppose this is interval AB where both A and B are closed. Any continuous function on this represented by this graph is a bounded function. So is bounded. Otherwise, the continuity would break down. Now, suppose, so to understand what happens if the domain is not compact. So, consider, see, the domain in this case can be not compact by being unbounded or not closed. Consider an interval I R then the interval I is either unbounded or not closed. So either it is unbounded or not. So let us look at the situation. I is unbounded. Then you have, look at I, a typical situation where I equal to 0 to infinity. Okay. Now on this, so you consider the function f defined from I to R defined by fx equal to x. Now easily observe that this is continuous but not for instance you can define, see, of course there exists bounded continuous functions for example, take for instance, so define fx equal to x belonging to now this is a continuous function but not bounded. Sorry, it's a continuous bounded function. So our statement does not say that all functions, all continuous functions defined from on I, all continuous real valued functions defined on I are unbounded. That is not the statement. There exists, see what you have is that there exists a continuous function on which is not bounded. Now we give another example. Suppose I equal to 0, 1, which is not closed and therefore not compact. Therefore not. Now define. So let us look at this function. Define this is well defined. Define and continuous. But not bounded. Okay, so there exists I mean, there are several functions on this interval which are bounded and continuous. That is not the case. What it says is that there exists a continuous function from the interval 0 to 1 which is not closed to R defined by fx equal to 1 by x, which is not, when there are several such functions which are continuous but not, because the graph of this function is some see that this is one, something like this, so that as this is the interval, so as x tends to 0, the function becomes infinite. Okay. On the other hand, suppose the interval is both bounded and closed, then what we can show is that all continuous functions defined on that interval are bounded. Okay. So let us now state the main theorem. So I hope I have made my points clear. Okay. So the theorem is this. Any continuous function f from a compact metric space x say to another metric space y dy So compactness play a role in the sense that combining continuity and compactness of the domain, it imparts the function in the boundedness problem. So let us prove this theorem. Which in turn tells that if X is compact and Y is a metric space, then you cannot have an unbounded discontinuous function defined on it. Okay, that's the other way of stating the same theorem. Okay, so let us prove this theorem. Okay. So fix y. Now for each n, consider the neighborhood B, Y, N, which consists of then by the continuity of F. See, this is the scenario. X, Y, and Y is some element here which is in the image of F. So what you have is, you have neighborhoods of this, which may lie entirely in Y or not even outside. Doesn't matter. Okay. Then what you have, suppose this is EYM. In the vector space, in the metric space Y. So I will put capital Y there. Okay. Now define, see, by continuity, what does it say? If X is the point that gets mapped to Y, okay, and this is f of X, there exists a neighborhood of X whose image under this is an open set in BYN. So you have or you can take because F is continuous, you can assert that the entire that we have shown, that if V is open in Y and F is continuous, then F inverse of B is open in X. So we can take this as what? Not only that, it may have some other portions also. Because there may be several points which get mapped to Y. So all the points here may go into this. Okay? So it's not that. So all these things constitute what is called F inverse of By Yn. That is because there may be multiple points from X which may get mapped to Y. So we are not assuming that it's a one-to-one map. Okay, so let Un and the set of all X belonging to such that F of X Dy okay, and you know that by continuity of F, Un is each n. Okay, what do you have then? Now you see that Un for every n. This is clear. And look at this collection Un. Then constitute an open cover it's an open cover for us. That's quite easy to check. And X being compact, so this is how we use compactness. That this cover has a final circle, which implies which implies you have UN1 say for that means there's a finite subcover. Let capital N be the maximum of N2. Then X equal to UN and f of x is contained in what does it mean? This implies is a bounded subset of that is bounded function Now, there is an alternative proof that you can give it out. I don't want to spend time on it. It's just a bit. It's almost the same thing that you prove because you choose one epsilon and then the idea is create for each point in y in capital Y. You take the one neighborhood of that, use their pullbacks. Now you see that the pullbacks will become a open sets which form a cover for X, which has a finite subcover, and therefore you can use F on that and then eventually prove that that is a F is a bounded function. Okay, so I think the details are there in the book, so I don't want to. I want to make some remark. Now, X may be chosen as any topology. But Y has to be a matrix. Because what happens is that if you ask the question fx is a part of Y and you are asking whether this is bounded or not. Okay, that boundedness concept is there in a metric space, but not there in a general topological space. That's the reason. So you cannot replace the condition that Y is a metric space by a general topological space. Now we look at some examples. Examples are what are called exercises. Let K be contained in R. Now every real value continuous function K is assume every real value continuous function then K is common. So that's a sort of converse of this result. Okay. Here what we have said is that if X is compact, then real valued functions, or for that matter in particular real valued functions defined on that, would become bounded functions. Now what we are asserting is that every real valued function on K is bounded. That is a condition that we are taking. Then we prove that K is compact. So now in this context, you look at the examples that we have considered earlier. Okay, right? What we have said is that if K is not compact, there exists unbounded continuous functions. Okay, so that's the negation of this. So what we are asserting now is that every real valued function defined on K is bounded, and therefore from that we can conclude that K is compact. Okay, so proof. Suppose is not compact, then either, because we are working in Rn, either K is not bounded or not closed, or both of those. Because the characterization of compact sets in Rn is that K is compact in Rn if and only if it is closed and bounded. So one of the properties should not be satisfied. Okay, or both. It doesn't matter. Right. Now in either case, we show that there exists an unbounded function. This is of course the converse of this result in a limited context, namely for functions defined from Rn to R. Okay. So we take the two different cases. So case 1, we have assumed that K is not compact, and we assume that the reason for this is that K is not bounded. R is not bounded. Now what you do is you take or fix any point P belonging to K. For any R positive, K is not the subset of okay, because otherwise it is a subset of some PPR, then it is going to be bounded. Okay, so K not bounded, we are retranslating. Implies for any R positive. Now consider the continuous function consider the continuous function the distance from x to p. P is a fixed point for x belonging to K. There is a distance function there. P x to make it unbounded, so it's something like this. It's a part of R. Then you are defining the distance function. This is d x. The distance function, it's a positive valued function. It's a non-negative function, and you see that you can show that this is continuous. So verify that f is continuous. Now this is unbounded. As I said, this is the sort of picture of K. K is not a bounded subset of, I am I have drawn this in R2. It's an unbounded subset. Okay. Therefore, the distance function that you define from P to X is a continuous function, is not, which is unbounded. Not. And this is a contradiction. And means we have produced a function which is unbounded on K, right? So by our assumption, all real valued functions defined on K are assumed to be continuous. So that is not so this gives a contradiction, and therefore this is not possible. Therefore the K is what you call bounded. Now we assume now the second possibility is that K is not closed. Okay, I'll make some remarks on this. Case 2, this is the case. Now once again we prove that, or we produce actually a function which is continuous but not bounded. Okay, so let us define this. Then where X is a point P belonging to Rn, which is not in K but is a limit pointer. So that K is not closed. Now we consider the function g of x defined by 1 by x. Now this is continuous on K but not bounded. That's easy to show because there is a sequence xn converging to A, xn belonging to K. Now you look at this sequence, that is 1 by or gxn. Now you see that this goes to infinity. That's easy to see. As so it becomes unbounded. The function g we have defined is a positive function. It's a non-negative function. Okay, so that's it. Okay, so in either situation, so this leads to, which is in this case A is closed. Now taking one and two together, A is compact. So that's the result. I mean, see this function. I'll just point out the example. Let's go back to our example, and you can see that. Okay. So this is the domain. This is the set that we are talking about. Now we are going to show that there exists, if it is, this is unbounded. How do we define the function? We choose a point P belonging to this. Now define a function which is, okay. What will be this function? So you are defining the function by this length. And you see that the function you have defined will, so this is the function. So this is what is called mod x minus p. And that is a unbounded function. This is unbounded. Now, the situation where suppose you take this case, then you see that 0 0 1. And then how did you define the function? So you take 0. So a equal to 0 in our theorem. Therefore, we define d a x or 1 upon dAx as. So in our case, this is going to be 1 upon. So in the present case, it is going to be fx is going to be 1 by x. So as x tends to infinity, you see this is what will happen. This is 1 by x, which is not 1. So in either case, you see that you can devise a continuous function which is not bounded. Okay. Therefore, it follows that k has to be both bounded and closed. Okay, bounded and closed. Therefore, k is compact. Now we prove another result on this about continuous functions. Okay. Suppose you have a function which is continuous on a compact subinterval of R. Real valued function which is continuous on compact subinterval. What will happen? So, the observation. Suppose and f is a function from entities. Then what we know from our calculus is that there exists, then f is bound. That is what we have proved in the last result. Further, say there exists numbers m and n such that fx lies between two numbers m and m. That is, the maximum value of f is capital M and the minimum value of f is capital M. That is, m is equal to maximum of or k and they exist. Now the question is, does there exist such that That means there is a point x1 where it attains its minimum value, and there is a point x1, x2 where it attains maximum value. Do you have such points? See, the answer is yes. Now, this is something which you cannot say if K is not compact. Suppose, for example, suppose K equal to 0, 1, which is not compact. Or and consider the function fx equal to zero. Now, you can easily see that what is the graph of the function? The graph of the function is this 1. And this is 1 here, and at 1, and is half. So it's something which drops down like this. You can show that this is monotonically decreasing. To take f dash, dash is what? By 1 plus x square. Okay, and you see that this is negative. Therefore, the function is decreasing. Okay, so f is a decreasing, and therefore f attains its maximum value zero and minimum value at 1, which is 1 and half. But 0 and 1 do not belong to K. So if K is not compact, this may not happen. Okay. Right? So that's the assertion that we are making. If K is compact, then the function attains maximum value. All continuous functions attain their maximum and minimum on the set K. Okay, right. See, it's quite possible that even on this you can have continuous functions where the maximum and minimum are attained. For example, you take this one. 0, 1, 0 and 1 are not included. This is not compact. Suppose you have a graph like this. A function has a graph like this. Something like this. See, the maximum value is here. Maximum value is here. It is attained at some point. The minimum value is here. It is also attained at some point. So it may happen that even on this function or on this non-compact set, remark compact. Or there may be continuous functions which attain maximum and minimum value, or minimum or both. Okay, as I gave the graph that you take the interval 0, 1 and then you define a function like this. Whose graph is this? Suppose this is continuous. Now you see the maximum is attained at some point here, and the maximum, so this is your x2 and this is your x1, where the minimum value is attained here. So this is small m. So there may be points where the maximum and minimum are attained. So let us now state the theorem. Okay, so we will state the theorem. Any continuous function from a compact matrix space K to R attains what you assert is that for all continuous functions, the functions attain its bounds. But if K is not compact, then this cannot be assured. There may be functions which have this property, but there are functions which do not attain the bounds on the space. Okay, let us now prepare the ground for the proof. So this is not the proof, but we are writing some metric space. Let be bounded continuous. And small m these are the notations. Okay, such that equal to m. So these are the notations. In fact, this is an explaining out what the statement of this is. This is explanation of it here. So this is exactly what we now we prove this. Now you know that F is implies F is common. This is the theorem we have. Now, under the assumption that K is compact and F is continuous, this is true. That is, there exists some alpha belonging to R such that mod Fx is less than alpha Therefore, you see, this is a bounded set of values in R. Therefore, its infimum and supremum exists. Exists. So if you take any bounded set of points in R, it attains its supremum and infimum. Now what we want to do is we want to identify this x1 and x2. We shall work with the supremum. Okay. Now we shall prove by contradiction where x is x2 such belonging to K you can prove for the infimum likewise. Okay. Right. Suppose by contradiction again, if there exists no point P belonging to K such that then we can construct the following sets. Define Un by the set of all x belonging to K for which fx is less than m minus 1. So this is the maximum value m that you are giving, and if this is not the supremum for this, see that you are taking m minus 1 by n, and you take Un as the set of all x belonging to K for this is true. This is the case. This forms open cover for K. Further, Un plus 1. then what you have is it has a finite subcover. K equal to sum A. Cos compact. And from that you can find out the particular. Now this is a contraction. Why it is a contradiction? Because M is the supremum. And for it would mean that this one, but our assumption our assumption now a similar proof can be worked out for this. Okay. And call that point x2. A similar proof can be worked out by assuming the other case, that is the minimum. Okay, so we stop here at this stage and then continue with it later, or possibly today afternoon or tomorrow. Thank you very much.